This video will continue our discussion of section 4.1. This is preliminary theory for higher order diffie-qs. So we have another idea here. It's a pretty simple idea. Assume that we have a linear nth order differential equation of that form. This is said to be homogeneous. We said this in a few videos back. But if it's equal to 0, it's homogeneous. Whereas the equation, notice that they take that same exact equation. You should have a y there in your notes, but they put a function over there of x, so not 0. So if that's not a 0, then it's called non-homogeneous. All right, we're going to refer to these quite a bit. So if I say the homogeneous form of the equation, then I need you guys to know that that means that it's a 0 on that right side. As if I say non-homogeneous, I'm meaning that the right side has some function of x that is not just 0. Okay, so definitions there. We have another notation here for you. In calculus differentiation, we end up just noting the derivative is just a capital D. So dy dx is just dy. Kind of just to simplify it for us. So for example, like here, the derivative of cosine 4x is negative 4 sine 4x. It's just the derivative. The reason we do this is because we want it to look like a differential operator, the operator being the term that we want it to look like. I want it to say, hey, I'm going to do this to this thing, to this left side, to this right side. Another form of this is that we had you guys write d dx like that. D dx is also an operator. I like d dx better than I like the capital D because d dx tells you what variable that you need to differentiate with respect to. I spend a lot of time in Calc 3 world, so that's why I prefer that. Here, we're going to just have an input-output. All right, we define nth order differential operator or polynomial operator. So what this is for a differential equation, we call it L. So what that is look, this is the nth order a function, d to the nth. So this is that nth derivative with that a sub n. And then we have the n minus 1 derivative with the a n minus 1. Remember, these things are just functions of x that were in front of our derivatives. And then there's that function of x again, first derivative plus a. Notice these have no y's, right? This is like writing this by itself, right? L is like, I'd put something in there, and that's what would go behind everything. All right. So since derivatives preserve constants in addition, then like one way to write all this, right, would be like this: L of y. There should also be a y right there. Sorry, these are going to be fixed in your notes. There should be a y right there. But that's what that means is you take all of the stuff that's in this line up here, and you're going to apply what it says to each part, to each function. So when we did y, we took that part, applied it to y, that part applied it to y, that part applied it to y, and this part applied to y in your notes, right? So that's what that means. And then we just say equals 0, and that's what we get. So this is the homogeneous form of diffie-q of an nth order linear. These are linear. That's like the big thing. It would make it linear because I get to just plug in that y and it takes the derivative of all of it. That's the whole point of it being linear. And then the second one is the same thing, except for there's a g of x on the right side. So literally, when I write L of y, it means all of that up here. So let me delete this, delete that. Oh, that y should be there. This is equal to L of y. It's plugging that L, the Y into the L. It's all applying. Okay, we're going to prove something. So hopefully you understand that notation. What this next theorem says, let y1, y2, yk, up to k, right, whatever k is, be solutions of the homogeneous nth order differential equation. So we have our normal, the equation we've been looking at, I don't want to say normal, but the one that we've been looking at, that is an nth order linear differential equation. It is homogeneous because it's equal to 0. And what they're saying is that we have several solutions to that diffie-q, y1 up to yk, however many that is. I could plug each one individually and I would get solutions. So the claim now is if I have multiple solutions, I can create a linear combination of those solutions with constants. Remember, that's what linear combination means. Is notice now we took every single y, we added them together, multiplied them by a constant. That's what the c's are, some constant multiple, and then we can add them together, and that whole new sum is a solution also to the homogeneous diffie-q. So if I have a list of solutions, I can create a new solutions by putting constants in front of them and add them together, and I get a whole new solution. So let's take a look at what a proof would look like, and I'm going to make this like not formal at all, really. Okay, um, let it's not going to be too formal. Let y equal y1, or actually, I guess we had to start. Let y1, y2, y dot 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 yk be solutions, and then this is where we're going to get lazy. To L of y equals 0. All right, so we have that. Each one of those, and actually we should do it like this. L y sub k equals 0 for all k, whatever k is, right? Up through some number. All right. If that's true, then we also have then L ck yk equals 0 for all k, where c is a constant, where c is constant. C sub k is constant, right? We have that. So if that's true, and that's true for derivatives, I guess we should say this instead. The derivative of that would be the same, right? And we could put, let's go ahead and put an n up here for all k and n. Sorry, I'm trying to get you guys to write less here. That's why I'm adding all this stuff in. Okay, if that's the derivative, then we also have that this is true. Okay, so if that's true, we also have what we could do with derivatives, right? Also, like this isn't formal, I would make this so much nicer looking. Also, the derivative of ck yk. Let's do derivative, not that yet. Let's do y sub k. Let's do, how should we do this? Y sub I plus y sub k. No. I got it. Here we go. Sorry for that. Y sub 1, y sub 2, dot, 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 or pluses. Y sub 1, one day we'll get it. Y sub 1 plus y sub 2 plus dot, 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 plus y sub k equals the derivative of each one. This shouldn't be 0, by the way. This should be ck, the derivative in yk. Let me fix that. And then this is going to be d in y sub k. 4. There we go. Think my brain was already on that next line. So the derivative of that, now hopefully you guys are making sense out of that. So the derivative of that is the same thing as taking the constant out of the derivative. Okay, and then if that's true, then I know that I could just do the next line, right? If I plugged in those, then I could factor C, all those C's out, which would give me the next line. And then the derivative of a sum is the same thing as the derivative. It like preserves the operation is what it's called for all K. We should have said for all K. Right. I'll never ask you to do a proof like this again. Also, that's why I'm making it very loose. So if that's the case, then L sub n of y sub 1, y sub 2, plus dot dot dot, plus y sub k is 0, because I could just split the derivatives there. Putting them together, using, because I know derivatives work like that, I can pull constants out. I can also take derivatives of sums. We have that L sub n, no n, no n, of y c1 y1 plus c2 y2 plus dot 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 plus ck yk equals 0 for all k. So we're done. Okay, I'll never ask you to do that again. That's a very rough proof. Probably not the greatest. We could have probably made it make much more sense. But the whole point of this is the reason that that exists, why I can do that, is because I know that for constants and derivatives, the constant can just come out front. And then I also know when I have like a polynomial, like x squared plus 3x plus 5, you guys do the derivative of each one separately. And then that's our answer. That's what we're saying here. That works here also for L, the left side of the derivative. So the whole point here, so we're going to look a couple corollaries. I think I said that wrong, but corollaries, there we go. Okay, I think math to this theorem, a constant multiple like this is a solution if that is also a solution to a homogeneous linear diffie. A homogeneous linear diffie always possesses the trivial solution. We talked about that at the beginning of this section. So if you take a look, this is a solution to that. So that means that this is also a solution, and you can see they picked a bunch of values as C's to get solutions. So we have an infinite number of solutions there. If we were to have a second solution, we could do CE7x plus C2, whatever the second solution was. So it's a pretty powerful theorem that if I have solutions to a linear homogeneous diffie, then I can create new solutions. All right, let's take a look at an example of this. It's a pretty simple idea. In my notes, I gave you guys a full page of this, but I didn't want to break it with the next page. So the functions y1 equals x squared and y2 equals x squared ln x are both solutions of the homogeneous linear equation, that differential equation, if you want to put that in there, on the interval 0 to infinity. And then it says by the superposition principle. So I didn't give it a name, but that's what this thing is. Superposition principle is that if I have multiple solutions, I can do a linear combination and I get a new solution. So taking a look here at this problem, they gave me y1, y2. So my new solution is as easy as this: c1 times x squared plus c2 times x squared times ln of x. We're done. That's our answer. That easy. So if you have multiple solutions and they tell you to come up with another solution, then we just put them together with C's. Now, there is something coming up, and it'll be on our next page, leading from our next page. Is this our only solution? You know, could this be like the main solution? Because if I let C1 equal 0, then I just get this, don't I? If I let C2 equal 0, then I just get the other one. So I can get every solution that was given in this picture, at least in the screen, I can get it from the highlighted solution here. I can get this one, I can get that one, and then I can get you a bunch of other ones. The question is how do I determine, can this give me the solution to every possible solution? If I pick C's, different C's, can I get every solution? Or is there a Y3? Or is there a Y4? How do we determine that? So that's what the next video will answer.